Hello, everyone. Welcome to today's live broadcast of sample preparation, extraction, and analysis of imported children's toys for Bisphenol A and phthalates. I'm Meg Evans, the Managing Editor of LCGC North America and your moderator for today's event. We're delighted to bring you this educational web seminar sponsored by Spex CertiPrep. Spex CertiPrep has been providing analytical chemists with superior quality inorganic and organic certified reference materials for almost 60 years. Spex CertiPrep is certified by Underwriters Labs for ISO 9001 and accredited by A2LA for ISO 17025 and ISO Guide 34, guaranteeing you will be receiving nothing less than the highest quality products available. Contact Spex CertiPrep today for all your inorganic and organic CRM needs. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can type your questions in the Submit Questions box located below the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window at any time by clicking on the Enlarge Slides button located below the presentations window. The slides will advance automatically throughout the event. If you experience any technical problems viewing or hearing this presentation, please click on the Help button below the presentation window. We are very pleased to be joined today by Patricia Atkins. Patricia obtained her degree from Rutgers University in 2004. While at Spex CertiPrep, she has been the R&D scientist and application specialist for the past 5 years. Prior to joining Spex CertiPrep, she was engaged in air pollution research in the Civil and Environmental Engineering Department of Rutgers University. She has given more than 30 presentations, webinars, and seminars on a variety of topics from laboratory water quality to heavy metals and pet food. Patricia has also authored dozens of articles, application notes, and white papers on analytical topics in the inorganic and organic testing fields. Her research interests encompass both the fields of organic and inorganic analysis using a variety of analytical techniques, including ICP-MS, GC-MS, and LC-MS. Additional speakers today will be Keith Tucker, Sales Manager from Spex Sample Prep, and Jason Keith, Analytical Product Manager from CEM Corporation, to comment and answer any questions pertaining to the sample preparation, digestion, and extraction of samples. Patricia, thank you for joining us today. Please go ahead and get us started.
Thank you very much, and I would like to welcome everyone to our sample preparation, extraction, and analysis of imported children's toys for Bisphenol A and phthalates. This is a topic near and dear to my heart since I'm a new mom, and I always want to know what my daughter is putting in her mouth. The study of Bisphenol A and phthalates has been about a decade in coming, since the 2007-2008 when regulations started appearing to control phthalates in children's products, Bisphenol A in water bottles, and things like that. But it's still a very topical area of study. This report from Science Daily in May of this year shows that another study has found phthalates are being taken up in infants' bodies from PVC flooring. So it's still a real big topic of debate and concern. Phthalates have been in production since the late 1800s and in commercial use since the 1920s. So very soon we will be living in a world where we've been dealing with phthalates for almost 100 years. They're used in plastic compounds anywhere from 10 to 60% by weight. They're used as binders, coatings, fragrances, and pigments. But the residue of these phthalates is pretty widespread. There was a study within the last 5 years showing that there was high concentrations of phthalates in household dust. This can produce a variety of potential disorders, from respiratory disorders, asthma, or reproductive disorders, especially because the phthalates are often considered to be endocrine disruptors. In 2009, the U.S. banned 6 phthalates from children's toys, and the Mexico, EU, and Japan have also restricted and banned certain phthalates from children's toys and child care articles. This is a very partial list of some potential phthalates that you can find in consumer products. The 6 that have been banned or restricted are these particular phthalates here, starting with the diene-butyl phthalate and going through the diisononyl phthalate. Some of the more common places you'll find some of these phthalates are in things like, of course, plastics, but insect repellents, soaps and shampoos, cosmetics, solvents, stabilizers, and of course plastic toys. Some routes of exposure where children might be in contact with phthalates include things we would not think of, like medical devices. Some medical devices can contain between 20 and 40% of DEHP by weight. There are also phthalate coatings on medications. Some of the enteric or slow-releasing coatings are made of different types of phthalates. Ointments, shampoos, lotions, and other type of infant and child care products can contain phthalates as softeners, fragrances, and colorants. You also have child care articles, pacifiers, bottles, plates, and spoons that can contain phthalates as softeners or different colorants. And of course, the object of our study today was toys. As far as regulations for phthalates go, there are quite a few regulations around the world banning or restricting phthalates. In the U.S., it's the Consumer Product Safety Commission's method, and for that method, DEHP, DBP, and BPA have been banned at 0.1% of each of those phthalates in all toys and child care articles. There are additional 3 phthalates restricted for oral care articles, the DINP, the DIDP, and the DNOP. The EU and Japan have slightly different regulations banning the same 6 phthalates or restricting the same 6 phthalates. The difference between their regulations is instead of having a 0.1% for each phthalate, it's 0.1% combined for the first 3 phthalates and 0.1% combined restriction on the oral care phthalates, the DINP, the DIDP, and the DNOP. Looking at bisphenol A, it's produced in a large quantity around the world, 3.7 million metric tons a year, and it was first reported in 1891. So again, we've been dealing with bisphenol A for quite a long time. It is also used in polymers, coatings, and epoxy resins. And it has been suggested since the 1930s to have estrogenic effects. There were studies in the 1930s on female rats that showed changes in reproduction, and it is also considered to be an endocrine disruptor. The EPA in the United States has put a general guideline for bisphenol A of 50 micrograms per kilogram of body weight per day, but there have been recent studies that show even smaller amounts, potentially as low as 0.025 micrograms per kilogram of body weight per day, can have an adverse health effect. The routes of exposure children have to bisphenol A primarily can be from food and food packaging. A lot of can linings that are used in cans with acidic foods, things like tomato sauce and soup and such, can have an epoxy lining that contains bisphenol A. There was also a lot of talk about bisphenol A and polycarbonate containers. So there was a lot of bans for polycarbonate baby bottles. And not too long ago, a liquid baby food formula study showed that there was 0.48 to 11 nanograms per gram of bisphenol A in the baby formula. A surprising route of bisphenol A exposure is paper labels and receipts. These are mostly the thermal transfer receipts, and not all thermal transfer receipts, but a good portion of them. These receipts use a process that has a coating of bisphenol A, free bisphenol A, on the surface of the receipts. And by handling these receipts, the free bisphenol A can get on the hands, the face, and in the mouth. Another surprising source of bisphenol A exposure, which I only just read about within the last few weeks, is currency. There was a study done showing that bisphenol A was found to be on most of the world currencies, with the highest suspect being the Canadian polymer, the new Polymer currency. These had the highest levels of bisphenol A. And a lot of the suggestion was that the currency, whether it be the paper or the Polymer currency, was having a transfer of bisphenol A from the receipts that we keep with our money or in our wallet or our purses, that the powder from the receipt was actually starting to settle on the currency. There's also exposure from bisphenol A from PVC piping. Again, with medical devices made with PVC. And finally, the subject of our study, toys. When it comes to regulations, the regulations have been changing quite rapidly this year when it comes to bisphenol A. Prior to July of this year, the U.S. as a whole had no position on bisphenol A as a regulation. It was up to each state to determine what their regulation for bisphenol A was. But as of July of 2012, the U.S. has banned baby bottles and sippy cups that contain bisphenol A. And at first, when I read the update to this legislation, I was like, well, that's really a great thing. Then I started also reading this was more or less instigated by companies that produce sports bottles, sippy cups, baby bottles, because they believed their products were safe, and they wanted to proliferate this image that they were free of bisphenol A and creating a safe product for the consumer. But either way, at least we now have a regulation for baby bottles and sippy cups that follows most of the rest of the world. The EU has already had in place a polycarbonate baby bottle restriction containing bisphenol A, as well as Canada. And last year, Canada deemed bisphenol A as toxic, which will now allow it to become an action item for more study and regulation. When it comes to actually testing for phthalates in the U.S., we follow the Consumer Product Safety Commission's method, which is the standard operating procedure for the determination of phthalates in children's toys and child care articles. This measures the 6 restricted phthalates and outlines a sample preparation, extraction, and analysis conditions. Now, any scientist will tell you there's a fine process that goes into testing a sample. You go through your initial acquisition of your sample, and some of us have samples that are whole and entire, and we have to decide what will be done with that sample, and some of us receive samples that are already processed in some form. But you do have to go through some sort of sample preparation and identification process, especially when it comes to these polymers. If you have unknown toys, they can be composed of many different types of polymer. So your first act would be to try to separate out the different polymers, then do a sample size reduction step, which could be as easy as cutting the sample up, or it could involve grinding, pulverizing, or some other method, maybe even a mechanical method, to get that to a nice powder. And of course, you want to do your identification. So if you have an FTIR or Raman, you can do identification, or you can do an old-fashioned identification using chemical analysis. Then you go through an extraction step. You could be as simple as a dissolution and a precipitation step, or you could go to a Soxhlet extraction step, or a microwave extraction step, which our friends at CEM will talk about a little bit. And finally, you need to apply an analytical method, be it GCMS, LC, LCMS, and you need to quantify against a known standard or against a curve. For us, the first step was our toy samples. We had 26 toy samples from discount or dollar stores, and we looked to group these samples into items with oral contact or without oral contact. We found several items that were definitely oral contact toys. We had some funny teeth, we had a snorkel mouthpiece, we had some party whistles. We also had some toys that if any of you have children, you know that invariably these toys are going to go in a child's mouth. We had our friend the rubber duck here, and I like to joke around that this presentation actually should be called The Story of the Rubber Duck. We also had our doll's head here and some figurines. As I said on the earlier slide, one of the first things that we had to do was separate these toys into component parts. To us, it was possible that this toy truck here had several different types of polymer or plastic, and we wanted to test each grouping as a separate sample. So we had 26 toys, which in the end turned into over 65 different samples. For this toy, we removed the stickers, but we did not remove the paint. And if you were going to follow up an analysis for metals, it might be part of a metals procedure to remove the paint and use that as a separate testing sample. So for this toy car, you can see we had the blue housing, which was potentially one type of plastic. We had a silver interior to the car, which was also a different type of plastic. We had a black undercarriage and the black wheels with the silver paint. For us, since we work with our sister company, Spex Sample Prep, it was a no-brainer for us. We decided that we were going to grind this sample. So in the Consumer Product Safety Commission method, it does suggest that you reduce the sample size to below 2 millimeter samples, or you grind it using a cryogenic type of method. For us, we use the Spex Sample Prep freezer mill, the 6970 freezer mill. We had an adapter which allowed us to do multiple vials at one time, so it increased our throughput of these toys very quickly. We also decided to use a polycarbonate vial, and we did look into potential contamination issues, but we actually found no contamination issues by using the polycarbonate vials. If you do worry about polycarbonate adding phthalates or bisphenol A to your analysis, you can run a quality control blank sample alongside your toys, and that will give you a little confidence about the potential for contamination, or at least eliminate the potential for contamination. Or you can use a stainless steel vial. The only problem with the stainless steel is if you are going to follow up with metals analysis, you might have a new contamination issue to worry about. One of the benefits to working with a manufacturer that does sample preparation is you can go to their website and find a host of different application notes. For our Spex sample prep company, we have quite a few application notes dealing with polymers. This one's about grinding polymers for qualitative and quantitative analysis. There are several applications on the Spex sample prep website that deal with the polymers, and we invite you to take a look at them if this is one of the challenges in your lab. But asking our company, Spex Sample Prep, for some tips and tricks about how you grind the different polymers, they went through their experiences with their customers, and they came up with a snapshot of some different polymers and how you could possibly treat them. You have something like a polycarbonate, which actually shatters pretty quickly, so it has a little bit less of a pre-cooling cycle. Then you go down to a PVC, and that particular type of plastic with additives could be challenging or problematic to grind, so that has a little bit more of a pre-cooling cycle. But this is a nice little guide to kind of at least start you in the right direction of where you want to be with your grinding. For our program, we used 2.5 grams of plastic, and we cut these plastic toys down to less than 5 millimeter samples. We ran 8 vials at a time using our multi-vial adapter, so we had high throughput. We pre-cooled for 20 minutes. We wanted to make sure those samples were nice and brittle. And then we had 5 cycles of grinding at 2 minutes a cycle. And each cycle had 2 minutes of cooling in between, so there was no heating of the plastic. It allowed us to have a very nice fine powder at the end. So what we ended up was this nice fine analytical powder. Something like the PVC duck was a very nice fine powder. Something like the whistle, which was a low-density polyethylene, was a little chunkier. That's a little harder to grind. So we got a very good result from our freezer mill. One of the things we did want to know was there really an advantage to the extraction by decreasing the particle size? We know that decreasing the particle size will increase the surface area for extraction, but does that really give you a better extraction than just cutting it into small pieces? Now, the method does call for less than 2 millimeters or a ground sample. So we took our PVC duck, our friend the pirate rubber duck here, and we took different size samples. We had sample sizes of greater than 5 millimeters. We had some around the 5 millimeter mark. We took some random pieces that ranged from 2 to 5 millimeters. And our prescribed 2 millimeter parts, and then finally our ground samples. We used 2 methods of extraction. We used a microwave extraction method, since we do have a CEM microwave on our premises. We also used the Consumer Product Safety Commission's THS extraction method. What we found is that the 5 millimeter parts, when put in the microwave extraction method, produced a somewhat clear, almost white extract, so it didn't really seem to have a lot of color to that extract. The 2 millimeter extract was slightly hazier with a slight tinge of yellow, but the powder really made the most dramatic difference in the microwave. We had a very dark yellow colored sample. For the THF method, you wouldn't have thought that the size of the particle would have really made a difference, since the entire particle is being dissolved. But the THF method, when we had our 2 millimeter particles, gave us just a slightly yellow, kind of opaque extract, where the powder that we had ground gave us more of a yellow and actually a slightly clearer extract. One of our challenges was actually to identify our polymers. We wanted to know potentially what type of plastics were we dealing with these toys. So I started looking at the groupings of the different plastics, and this should be a very familiar sight for many of us. These are the recycling codes for the different types of polymers. And by looking at the different uses for the polymers, we were able to eliminate some of them as potential toys, but we were also able to isolate which ones were probably going to be the highest percentage of the toys. Things like our polyethylenes, our high density and our low density polyethylenes were very commonly used for toys, so we were expecting to find things like that. As well as PVC, very common use in toys. Something like a polypropylene, we probably would not see as much. It was more for food containers and things like that. ABS was a possibility. That's an extruded material. It's most commonly what we think of as Lego material. In the end, what we ended up having to do was create this table of polymer characteristics for our target polymers and decide how we were going to set up our testing in order to identify the different polymers. You can use a mechanical method or an instrumental method to determine different types of polymers. You can use FTIR or Raman, but not having those in-house for us, we had to kind of go old school and set up chemical and physical testing to isolate our polymers into groups. And since we were doing a microwave extraction on our polymers, we really wanted like plastics in the same batch. What we ended up with was this kind of convoluted flow chart, which allowed us to do different density and solubility tests to give us tentative identifications for our different polymers. In the end, what we found out is the highest percentage of polymers in our toys were our polyethylene polymers and our PVC. We did have a couple of polycarbonate samples, as well as an ABS and a polypropylene. We also had a cloth sample, which was the doll's dress, and a silicone sample, which was the nipple of the pacifier. Overall, we decided to focus our analysis on what we were deeming to be some of the dirtier plastics, like the PVC, and some of the cleanest plastics, which we believed were the HDPE. For our HDPE toys, our high-density polyethylene toys, we had our police and fireman figures. We also had several of the toy car parts turned out to be high-density polyethylene, things like the black base of that car, the black wheels, and the silver interior. We had a very large amount of different PVC toys. We had things like our snake figures and our dinosaur figures and our marine shark and dolphin. We also had our 3 cartoon figures whose identity we've obscured here to protect the innocent. We also had quite a few toys that had potential or possible oral contact. You had your snorkel, which was definitely designed to be put in the mouth, as well as those party teeth. Then you also had your rubber duck and your lion, which anyone who has a toddler knows those are the first thing at bath time to go in the mouth. Then our task was also to try to figure out what were the potential contaminants or dangers of each of the different types of plastic. Something like a polyvinyl chloride has phthalates added to it, possibly bisphenol A, and heavy metals. A high-density polyethylene or a low-density polyethylene has very small amounts of additives that are put with it. Our polycarbonate has a danger of bisphenol A, and some of our other plastics have some additional considerations like acetaldehyde, antimony. Our next step was then to go to the prescribed method, the Consumer Product Safety Commission method, and choose a method for extraction. You have quite a few choices if you're following this method. You could be doing a oxalate extraction or an ultrasonic extraction or a microwave extraction. There is also a wet extraction method prescribed within the Consumer Product Safety Commission method, but this method is very polymer specific, and speaking with some of our customers, they've had a hard time because they did not realize that this method, if you look in the text of it, it says to precipitate any PVC polymer. So this method really works only with the PVC materials to get the result that you're looking for. For this method in general, you use about 0.05 grams of sample to about 15 mils of solvent minimum. But what we found with our PVC toys is that they don't always precipitate with the 15 mils of solvent. What we have here is a picture of 3 different vials. On the left is our CRM material, which does not contain anything but 6 of the restricted phthalates. It doesn't contain any colorants, any binders, or any other types of material which might be added to a PVC toy. On the right are 2 PVC toy samples. When we added our 15 mils of solvent and we tried to precipitate out our PVC material again, we were unable to get the PVC to fully precipitate out of the solution. So if you're looking at the Consumer Product Safety Commission limit, which is 0.1% of each of these phthalates, or 1,000 micrograms per gram, if you're injecting this 15 mils straight, you're looking about 3 ppm on your GCMS. If you follow the method even further and you dilute it according to the method, you're looking at 0.7 ppm. And for most of us to reliably look at the 0.7 ppm on our GCMS, we're going to use a SIM mode. We did not want to use a SIM mode. We had never seen these plastics before. We wanted to do a little bit of analysis, and we wanted to see what else was in there besides the 6 restricted phthalates. So we did not. We decided to use scan modes because, as I said, we wanted to see, are there any other additives in these plastic toys? Were there any phthalates which potentially could be misidentified as one of the restricted phthalates but was not a restricted phthalate? And what happens if the levels were very low? Would we miss those entirely? Something like a Bisphenol A might be potentially very low, and we would not be able to see this if we use SIM mode. We also wanted to know what was the extraction efficiency of the different methods we were choosing to use. We were able to test this by taking our Spex CertaPrep CRM. This is a polyethylene CRM, which has the 6 restricted phthalates in it. And we ran it using the THF dissolution and precipitation method. What we found for the polyethylene is we recovered 50% of what we were looking for. So that showed to us that, for at least for the polyethylene, that this THF dissolution was not effective. So then we developed a CRM for PVC. We also ran it again using the Consumer Product Safety Commission's suggested method of the THF dissolution, and our recovery went up quite a bit, from 83 to 94%. But what we personally found was not all of our PVC material was precipitating out 100%, and we started having GC contamination issues, and our reproducibility started going very, very far away from the RSD. So when we did 10 subsequent injections, our RSD values climbed. So you can see they ranged from 35 to 60% RSD. So we decided to take advantage of our microwave unit, and I think I'll hand it over to Jason for a minute to talk a little bit about extracting plastic polymers with the microwave.
Thank you. When you're extracting polymers, you have a lot of good choices here when you're working with the CEM. You can see here we have an application note for one of our polymers. We have many application notes available depending on the type of polymer you're interested in extracting. An example here is high-density polyethylene. You can see here that the application note gives you some good starting recommendations for the conditions that you'll need to get a good extraction. For example, in this application note here, you use a good starting mass for the high-density polyethylene is 2 grams. In terms of reagents, we recommend using an acetone cyclohexane in a 7:3 ratio. In terms of the volume, 25 mils is a good starting volume. And you can see here on the right-hand side, we recommend the type of instrumentation you should be using for this as well, along with the vessel. You'll see here that we have a picture of our Mars system, as well as a green chem vessel. We can also use an express vessel for this as well. With this information, we also give the microwave power applications as well. We provide information such as your ramp and hold times, the extraction temperature that's needed to be able to achieve a good recovery and have a good RSD value. One of the things that's really important to note with this application for all extractions is that you need to make sure that you have your temperature and reagents precise. You want to make sure that you don't dissolve any of your sample. The goal is actually to extract it and not dissolve it, and you want to make sure you get all of your organic components out so you get a good recovery. I'll be happy to answer any other questions later in the presentation if you have anything questions about extraction. I'm going to pass this back to Patricia to continue the presentation.
Thank you very much. That's a good starting point from where we went with our microwave method optimization. We actually did look first at the methods developed by CEM, and I did speak to their application specialists at CEM to just verify some of the tasks we wanted to do to extract these polymers. And we did end up using the HDPE, or the high-density polyethylene method that, as it was written, using the cyclohexane and acetone. We found a very high recovery, about 95%, when we used our CRM and that particular method. When looking at some of the other methods, we looked at an LDPE method. That is an IPA solvent base, again with a very good high recovery. And then we had a PVC method written by CEM, which prescribes an ether as an extraction matrix. We decided we didn't want to run ether, so we looked for an alternate matrix. We also started looking back to the other methods we had just run, and we had the choices of cyclohexane, acetone, and IPA. We did not want to run the acetone because we were afraid the acetone would totally dissolve the PVC, and it would kind of defeat our goal, which was not to dissolve the polymer. So we did a series of experiments at different temperature programs, different solvents, and we found one that gave us a very high recovery rate. It was going to a temperature of about 130 degrees C with a 50-50 mix of IPA and cyclohexane. At this point, we found that the polymer did not dissolve, it did swell slightly, and it gave us a very good recovery of 95 to 105%. So the methods we used for the HDPE was the same methods prescribed, 10 mils of the cyclohexane at 30-70 mix. We decided to use less sample, 0.2 grams of sample, and we ramped over 10 minutes to 140 degrees C, where we held for 10 minutes, and we did use stirring for these samples. For the PVC, we have our optimized method, which was 10 mils of the solvent, the cyclohexane IPA at 50-50, 0.2 grams of sample, ramping over 10 minutes to 130 degrees C, and we held it for 10 minutes. Again, stirring was used. What we found for us was a benefit of the microwave. We were allowed to use then smaller amounts of solution, higher amounts of sample, and get a very efficient extraction out of it. We were able to see the very small phthalates and things like Bisphenol A without any problem. We were able to see them in scan mode, as I said. And when we found that some of the phthalates were out of our analytical range, they were just too high, we were able then to safely dilute those samples down and retest them to get them into our analytical range. One of the best parts is we saw very little carryover on the GCMS, so it gave us great reproducibility. And because there was multiple spaces or multiple sample vessels, we were able to have a very high throughput. Our RSD for the microwave method was very good. You can see that our phthalates that we monitored here had anywhere from 2.5 to less than 0.4% RSD. What we used was a GCMS in scan mode, and we used a CV5 capillary column of just standard dimensions. We monitored for the 6 restricted phthalates as well as Bisphenol A. We did primarily quantitate on the 149 ion for most of the phthalates. We did look at 213 for Bisphenol A. One of the exceptions is the coelution of the two larger phthalates at the end, the diisodecyl and the dinonyl phthalate. For those phthalates, we did monitor alternate ions. And of course, since we are a standards company, we had a whole range of standards to compare against, including some CRM materials. That polyethylene QC standard that we use to calculate our recoveries, as well as a polyethylene blank, and then a new PVC standards that we created just for this project to monitor our extraction efficiency of PVC. Now I'm going to talk about what we found in some of these toys. I'll start with the HDPE toys, which, to refresh your memory, were the plastic figures and some of our toy car parts. In our toy cars, we found that there was only one restricted phthalate in the toy car parts. This was the DNOP. And the level we found this DNOP at was way below the 0.1% or the 1,000 microgram per gram level that was allowable by the method. We were able to discern that there was no measurable BPA, which we didn't expect, to be honest. One of the strange things, or not so strange things, that we found, but we were able to see with our scan mode, is higher alkanes were being extracted out of the wheel of the toy car. For our PVC toys, we had a lot broader range of results. For our toys without oral contact or possible oral contact, we found a whole host of different phthalates, but the most prevalent phthalate in all of our toys was the DEHP. You can see here of all of our PVC samples, starting with our lion and going through with our friend the rubber duck, and the level of DEHP, if you compare it to what's allowed by the Consumer Product Safety Commission at 1,000 micrograms per gram, almost all of our toys exceed that level. More concerningly is the snorkel mouthpiece, the doll's head, and the duck. The snorkel mouthpiece, which is an oral contact toy itself, but the doll's head and the duck are also potentially oral contact. They're not designed to be put in the mouth, but as we all know, they end up in a child's mouth. We also found some of the other restricted phthalates. We saw DINP, DIDP, and DNOP. For the levels of DNOP, again, they were below the Consumer Product Safety Commission limit. In one particular sample, though, the donkey figure, we found very high amounts of the DINP and the DIDP. If we looked at the total phthalates, you can see the potentially highest values you could get for the phthalates for some of the regulatory methods. Potentially the highest amount of total phthalates you can have in the EU or European method is 0.2, assuming you have 0.1 of the oral contact phthalates and 0.1 of the general restricted phthalates. And for the US, you could potentially go up to 0.6 or 6,000 micrograms per gram total, assuming you are within the limits of 0.1% for each. And as you can obviously see, that most of these toys would violate both limits. Since we were running in scan, we were able to see the Bisphenol A, and we found that we had three PVC toys that contained measurable amounts of Bisphenol A, with our Triceratops figure at about 200 micrograms per gram, our friend the rubber duck at almost 800 micrograms per gram, and the doll's head at almost 1,200 micrograms per gram of Bisphenol A. One of the interesting things we found in our scan mode was alternate plasticizers, specifically a butyl citrate and tributyl acetylcitrate. We found this in 9 of the 17 PVC toys. And in 7 of those toys, the amounts were large enough to be in percentage quantities. The highest we found of these two particular alternate plasticizers was in our lion toy. And it was also very interesting, the lion toy had no phthalates, but it did have high percentage amounts of the butyl citrate and the tributyl acetylcitrate. So if we look at conclusion of what we found in the PVC toys, we found small amounts of some of the other restricted phthalates, below 50 micrograms per gram of the DBP and the BBP. Our DEHP was our most detected phthalate, with 15 out of 17 of our toys containing the DEHP. We also found 12 of the 17 toys would be considered over the consumer product safety limit of 0.1%. The highest amounts of DEHP were in our friend the rubber duck, but we also had that snorkel mouthpiece that came in at 14,000 micrograms per gram. The lowest amount of DEHP was found in our Lion, which I said had no other phthalates in it, but did have high percentage amounts of those alternate plasticizers. Now I'm going to go over a little summary of everything we did in this experiment. Our toy preparation included separating the toys into the different parts and removing any of the paint and stickers and paint. Now, we did not remove the paint, but if you are going to follow up with metals, you're going to want to probably remove the paint according to your method. We reduced our sample size to powder or pieces less than 2 millimeters. We felt we needed to identify the plastics in order to best determine what extraction method we were going to use, which solvents we were going to use, what temperatures we were going to use in the microwave. If you use the Consumer Product Safety Commission wet method, it should be really used for PVC only. And according to the experiment we did with polyethylene, it didn't work as a good extraction method for our polyethylene material. Our polyethylene came at extraction of 50% recovery. You can always check your extraction efficiency by using a CRM or a QC sample. For extraction, we tried multiple different methods allowed by the Consumer Product Safety Commission, and we ultimately decided upon an optimized microwave extraction with over 95% efficiency for our polyethylene and our PVC methods. When we look at our results, our HDPE toys only had one of the restricted phthalates, way below that 0.1% level, and that was the DNOP. But we were also able to see some of these higher alkanes. For our PVC, the most prevalent phthalate was the DEHP, and there was a high concentration of DEHP in the majority of our PVC toy samples, many of them in excess of the Consumer Product Safety Commission limit. Two of our oral contact samples had between 10,000 and 30,000 micrograms per gram of DEHP. We also found Bisphenol A in 3 of our PVC samples, including our doll's head, which topped out at 1,200 micrograms per gram of Bisphenol A. And we found some alternate plasticizers in our PVC. And that is the conclusion of our results. I would like to acknowledge those who helped with this project, including the Spex CertiPrep chemists, the specialists over at Spex Sample Prep for all of their help in grinding these polymers, as well as the CEM Corporation for all the help and assistance they gave us in developing or optimizing the microwave methods we used. Now I'd like to invite Jason for any last words or comments he would like to give.
CEM would be happy to help out anyone who's going to be doing any extractions in the future of any type of polymers. We have a well-staffed technical team here that's worked with extractions for many years. They can answer any technical questions you may have about sample types, type of reagents you may need, or the microwave conditions. Feel free to give us a call at our 1-800 number there on the screen, or feel free to email us. We'll make sure to get back to you within less than a day or so. If you have any questions about the sale or purchase of a microwave system, our sales team would be happy to help out. You see here on the right-hand side the picture of our new Mars system. You saw the picture of the one in the application note. That was our older Mars. This is a brand new system that was just recently released. It's called the Mars 6, and it's designed for extraction of samples up to about 40 samples at one time.
Thanks a lot, Jason. And Keith, our friend Keith here is starting to lose his voice from laryngitis, but I'll give him the opportunity to croak his way through a few last remarks.
Thanks, Patty. Thanks, everyone, for logging into our webinar. Sample preparation has several different mills and grinders for preparations of all types of polymers and materials. We have a free demo program that can be used at your disposal. You can give us a call at our 8855 number, or you can log on to our website where you can actually log on and speak to someone live on our live chat. At any time, if you have need any assistance with your sample grinding or sample preparations, feel free to give us a call. We look forward to hearing from you.
Thank you, Keith. And of course, last but not least, Spex CertiPrep has been providing standards to the analytical community for over 40 years. And if you have any questions on what standards or CRMs are available for your types of analyses, feel free to call us or log on to our website or email us, and we'll be able to get back to you with some help with the applications or the different standards that you would need. I would like to thank LCGC for hosting this event for us, and for all of you for attending and taking a look at some of what we've been doing here at Spex CertiPrep with the help of Spex Sample Prep and CEM. And I guess I will turn it back over to the moderator now.
Thank you, Patricia, for that informative presentation. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. As a reminder, text chat is located in the lower left-hand side of your screen. To submit a question, type your question in the small text box at the bottom, and when finished, click the Submit button. We'll answer as many questions as we can. Now let's move into the live question and answer portion of the webcast. Our first question is for Jason. Can microwave break the polymer's structure?
Oh, is Jason there?
Yes. Sorry about that. Yes, microwaves actually cannot break the polymer structure. They actually cause a rotation of the molecule, which causes a heat increase within the molecule itself. So there's actually no breaking of any bonds within the actual structure of the polymer.
Okay. Our next question is for Keith, if he's feeling up to it. How do you keep PC sample container from becoming brittle when cooling?
PC container, I'm sorry?
Yeah, how do you keep it from becoming brittle when cooling?
Well, you have two options when using our freezer mills. You can use our polycarbonate cylinder, or we have a steel cylinder. If you have any concerns of the polycarbonate cylinder breaking for some reason, but the grinding is actually done on the end plugs and not on the polycarbonate cylinder. So typically your materials are going to be ground on the end plug, so it will not have any impact on the polycarbonate cylinder. Doesn't have any impact on being brittle or anything. It's not going to be hit. There's occasionally you might have a really hard material that the impactor that shuttles back and forward doing that grind can hit a hard piece of polymer or something and refract off of that, hitting the polycarbonate cylinder, causing it to crack. Now that could happen, but to avoid something like that, we have an all-steel cylinder that will alleviate that problem.
Okay, the next question is for Patricia. Did you detect any other replacement BPAs, for example, BPS, et cetera, since you weren't using SIM scanning?
That's a good question, and I really should go back and look through my data files and see if we saw anything like that. At the time, we were only really focused on the Bisphenol A, some of the alternate plasticizers, which were in huge amounts. They were very hard to miss. But something that would be kind of on the small side, like a Bisphenol F or a Bisphenol S, something like that, we really didn't look for. But now that the question's been suggested, I should go back and see if any of those compounds get their spectra, and go back and see if I can find any of those compounds in my data. So that's a good suggestion. So no, I didn't do it, but recently there has been a lot of talk about the alternate bisphenol compounds, and it's not a bad idea for me to update my presentation a little bit and go back and take another look at them.
Okay, I have another question for you, Patty. How do you verify if the plastic is dissolved or not during extraction?
Well, it's pretty clear when it's not dissolved. When the plastic is basically opaque and sitting in your vial, then you can pretty much tell that it is not dissolved. Something during a microwave extraction, it was almost an all or nothing kind of extraction, whether it dissolved or not. When we dissolved some of the PVC samples by accident while we were trying not to, it was very clear when the liquid came out that there were no particles or no particle pieces left. So that pretty much eliminated for us the whole, is it dissolved or not. When it came to are we partially dissolving a sample, that's a little harder to determine. What we try to do is look at the different types of polymer and their melting point. And we wanted to keep our system just below that melting point, or if possible, try to keep it below the melting point or any point where it was going to potentially dissolve with the added solvent in it. So that's where really knowing what type of polymer structure you're dealing with and how it reacts to heat and solvent would be quite helpful. If you pick solvents that will not dissolve the polymer and you keep melting point in mind when you're setting a temperature program, you should really reduce the amount of potential for polymer to dissolve into your extract.
Okay, I have another question for you. Which of these 6 or 7 plasticizers are most likely to be found in toys?
Well, according to what we've found in our PVC toys, the most common is the DEHP. And I've actually spoken to quite a few people involved in plastics research, and they say DEHP is a very, very common plasticizer. They do also see some of the larger plasticizers, the DNOP, the DIDP, DINP. But for the most common one, it's the DEHP.
Okay, the next question is for Jason. What is the compatibility of different solvent or solvent mixtures in the microwave? Basically, are there any limitations when using the microwave?
When you're using the microwave, one of the most important things is you have to have a solvent solution that is polar. And the reason why is you need to have some rotation of the molecule so that it's actually heated by the microwave energy. So that's why a lot of times we use a solvent mixture. You can mix a non-polar solvent with a polar solvent so that it actually does give the solvent mixture some polarity, and then it will heat. If you run a non-polar solvent in there, for the most time it won't heat very well at all, and you'll never reach any type of temperatures that you need to complete an extraction.
Okay, I have a question for Patricia. What column did you use in the GCMS analysis?
We used a CV5, or depending on what brand you are, it's CV5 for us. It's basically a DB5. It was a very standard MS column, and I do have the dimensions in the presentation.
Okay, and another question for Jason. How many samples can be run in the microwave during a single run?
It depends on the type of vessel you use. There's a choice of 2 or 3 different types of vessels you can use for extraction. The one is the green chem vessel. That's very commonly used. That can run up to 14 samples during a run. Typical run time is less than an hour, including the cool down time for those 14 vessels. You can also run the express vessel. That's a higher throughput vessel, and you can actually run up to 40 samples at one time with that, and also under an hour.
Okay, another question for Jason. Do the microwave extraction vessels only come in Teflon?
In terms of the materials that are used for the vessels, the express vessels come only in Teflon. The green chem vessels can actually come in Teflon or as well as a glass. So you have a choice of 2 different types of materials depending on if you want to use a Teflon material or not.
Okay, I have a question for Patricia. Why grind polycarbonate when you can completely dissolve a PC sample?
Well, for us, we really didn't want to dissolve the samples themselves because we did find, it might be due to the age of some of our GCMS systems, but we did find that there was carryover of the polymer when we were trying to dissolve it and then try to precipitate it out. I have not ever run a polycarbonate dissolution and precipitation method. I'm sure someone out there has tried to create a method for it or has a method for it. I just found that if I was able to extract it efficiently without making the polymer part of my extract, it just was better overall for our analyses.
Okay, I think we have time for one more question, and it's for Patricia. Was your GCMS analysis method done using internal standards or external standards with a Cal curve?
We did them both ways. We do have a series of internal standards that we very commonly use in our labs, and we ran them that way. We also did try running the internal standards suggested in the Consumer Product Safety Commission method. And then finally, we did have external standards that we ran alongside. One of the problems we found with, it actually became an indicator of how much polymer was dissolving into our extract, was with our PVC samples, if the PVC polymer was extracting or dissolving into our extract, one of our internal standards started being suppressed. So when we started seeing a suppression of one of the internal standards, we knew that we were getting a little bit too much of the PVC polymer. In fact, one of the higher temperature programs we tried, I think it was 150 degrees C with the microwave extraction, gave us fairly good recoveries, but one of the reasons we decided not to use it is that we saw this suppression of one of our internal standards, and we decided that since the 130 degree temperature for PVC was perfectly efficient and gave us a very good recovery, there was no need to potentially dissolve more of that PVC into our extract.
Okay, thank you all for those insightful answers and for your presentation today. Unfortunately, we're out of time. Any questions that we did not get to will be answered by our speakers via email. I want to thank the audience for your interesting questions and participation in today's event. I would also like to thank our sponsor, Spex CertiPrep, for making today's educational webcast possible. Please note this webcast will be available for on-demand viewing through September of 2013. You will receive an email from LCGC alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. See you next time. Goodbye.